Okay, here we have another example of a partial fraction decomposition. Notice this time, however, that we have a cubic function in the denominator, x cubed plus 4x. So this is going to correspond to case 3. When I factor the denominator, I'll notice that I can get a linear factor of x and a quadratic factor of x squared plus 4. So the way that we break that up is that the linear factor just gets a constant in the numerator coefficient, and the quadratic factor gets both a linear and a constant factor. So that's why that x squared plus 4 has a bx plus c up there. To solve for a and b and c, I'll need to clear the fractions. So I'm going to multiply everything by x times x squared plus 4, and that will give me a times x squared plus 4 plus the quantity bx plus c times x. Time to distribute over there on the right, and that will give me 2x squared minus x plus 4 on the left, ax squared plus 4a, bx squared, and cx. Next up, we've got a group by degree. So I've grouped together ax squared and bx squared. Cx is the linear term, 4a is the constant term. Now it's time to equate the coefficients. So I'll notice that on the left, my quadratic term has a coefficient of 2, and on the right, my quadratic term has a coefficient of a plus b. On the left, my linear term has a coefficient of -1, and on the right, a coefficient of c. And then my constant term has a coefficient of 4, and on the right, 4a. So I write my system of equations equating my coefficients, and I'll get the following. 2 equals a plus b, -1 equals c is automatically solved for, 4 equals 4a. So I can get out a by dividing by 4, and then I can plug that back in, and I can get out b as well. So now I know that -1 is equal to c, 1 is equal to a, and 1 is equal to b. So now if I go back to my integral, excuse me, I can split it up as an integral a over x dx plus the integral of bx plus c over that quadratic denominator x squared plus 4 dx. The first guy, plug in a equals 1. The second guy, plug in b equals 1 and c equals -1. The first one's going to integrate nicely, but I'm going to have to do something fancy with the second one. I'm going to go ahead and split that up into 2 separate integrals. So leaving the denominator the same, I can integrate x over x squared plus 4, and then I can introduce a third integral, -1 over x squared plus 4, just splitting that guy up into 2 separate terms. Now my middle integral, x over x squared plus 4, can integrate using a u substitution, and I just have to take care of the constant 2 in my du. And my third integral is going to actually integrate using a special inverse tangent. So we know that 1 over x squared plus 1 has an antiderivative of tangent inverse, and here we just have to do a little u sub in that tangent inverse integral and treat that 4 as, say, the constant a, and take care of him. And so you'll see I wrote the rule down here. If we're using something that's similar to inverse tangent, we just take into account the change in the constant, and you can see that we end up with a coefficient of 1 over a and also x over a inside the inverse. So if we put all those pieces together, we end up with our very first integral that was hanging out this whole time waiting for us, integrating to natural log of x. Then using my u sub, there's my coefficient 1/2 from du, and then 1 over u du. There's that special tangent inverse antiderivative. I went ahead and evaluated natural log of u, and then I'm writing in pen, but I realized as soon as I put that first absolute value bar here that I no longer needed it because x squared plus 4 is positive, but I committed to it. I'm in pen, so you could put parentheses there or the absolute value signs. But the final solution is natural log of x, absolute value x, plus 1/2 natural log of x squared plus 4 minus 1/2 tangent inverse x over 2 plus c.